Hey, what's going on, guys? Today we're going to be going over LeetCode number 62, unique paths, and talk about a dynamic programming solution to it. Um, in my computer science club today, we went over problems like this, and I thought it'd be useful to some of you watching my videos to understand my take on these solutions and how to solve the harder ones. So I guess to remind us of last video, we covered the basic concepts of dynamic programming. We talked about a staircase problem where you have steps and you can take one or two steps. You can climb one or two steps at a time, and you're seeing how many ways to reach each step. And then when we figured that out was we scaled the problem down. We looked at just the first step in the staircase. Kind of connected there. A little bit of staircase, yeah. We just looked at just the first value, and we found that starting at the ground, there's only one way to get there using combinations of steps 1 and 2, and that's 1. And then for the second one, we found that there was 2, and then we used previous solutions to smaller subproblems and combined them to find larger solutions. So in order to find the value of this second index, I wonder if the index is in a different color. In order to find the solution to the second index, we just combined the first two indexes, because if we look at the combinations to make the first index, we have 1 plus 1 and 2. And for the first one, we have this. But to get from the first index to the second index, that's a jump of 1. So we can add a plus 1 to the end of all these to get a combination that is valid for this second index. And we can also add a plus 2 to this first thing to get a combination that's also valid for this second index. And then we combine these values to get a number of 3. And then this program kind of continued, giving us 5, 8, and so on and so on. And yeah, and so if you are curious about this, I just coded the solution to this in a different video called The Essence of Dynamic Programming. So if you're curious about that, check that video out. But for this problem, we're going to be going over unique paths, which is a very similar problem, and I'd say it might be simpler to people who haven't approached problems like this before, but definitely very complex. And so the first thing we're going to do is, or actually, first of all, if you haven't tried this problem on your own, I'd recommend trying it right now. Try using that concept I just explained, where you scale the problem down and look at smaller ones, and then base your answers off of those in order to find the solution. So try that, but I'm assuming you've already tried the problem. But anyway, we're gonna read the directions anyway. There is a robot on an M by N grid. The robot is initially located at the top left corner, which is all the way up here, 0, 0. The robot tries to move to the bottom right corner, which is length minus 1, length minus 1, which is bottom right. The robot can only move down or right at any point in time. And this is very useful information right here, because if they can move up and down, they could theoretically just keep going up and down, or there's so much more to consider. But because we know each step is always going to be closer to the finish, we're limited in the paths that we can take to reach there. We can't go down, right, and then up, and snake. It has to be like a down, over. It's like a staircase-ish pattern. And then given two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. Test cases, yeah, okay. So now we have m and n, which is going to give us a 2D array. And so in order to scale this problem down, I guess we first we think big scale. We think, what are we calculating? We're seeing all the ways we can reach this finish, which if we were to calculate it by hand, it would take forever. But to think about it, it would be, first one would be something like this, then maybe something like this, then maybe something like this, and then something like this. And it would just go on, and we could go forever. It'd be so many different ways to do it, and it would just take way too long to do this by hand. So instead, we're going to think about sub-problems. Because in order to reach each square, you need to have been to a different square ahead of it. So to scale this all the way down, let's look at m and n with a value of 1. This gives us a matrix which is very small. It's 1 by 1, which would be this square right here. So if this was both the start and the end, there would be, I guess, only 1 or 0 ways to visit the finish, however you want to think about it. They wouldn't even move, and they'd be there. Now, if m and n was 2 and 1, let's say it was this box right here, and this was the star, how many ways are there to reach here? That would be 1. There's only one way to reach there, because it would just be a straight line there. And if n was 2, so if the height was 2 and the box looked like this, we'd know the same thing. There's only one way to reach this star, which is just a straight line there, which is also 1. Now, this is kind of like the base case. So if you did our last problem, we initialized part of the array to 1 and 2 in order to be able to base our later answers off of that. And that's kind of what these are. We just figured this is very small base cases. Now we're going to expand it slightly larger, which is where the problem complexifies. And that's when we have a 2x2. And now for this, there's actually 2 ways to reach it. There's here and here. You can go that way, yeah. Those are only 2 ways. But the way I want you guys to think about it is not like how many ways can we reach this square, but from where can I reach this square? What squares have access to this square? Like what would be the last move that you would have made to get here? And the last move you would have made to get here always has to be a down or a right. In order to get to this square, you have to go to the right or down, because those are the only possible moves you could have made. You know what, you couldn't have come up in or to the left in, so we know you must have come from there. And because of that, we know that all the possibilities, however many ways you get here, all we do is we add one more turn to get here. And this is similar to the other one where we added a 1 or a 2, but now we're adding direction. So for this square right here, you did a right to get there, right? And then for this one, you just went down 1. So you've down. But now what we're saying is all we need to do is add 1 step to any combination of these moves to get here. And that was plus a down for this one. All we have to go down from all these combinations and go right from all these combinations. So anyway, we reach that square, we reach it using all of these combinations, and then we just go to the square. And if we combine these 2, we get 2. Oh, hold up. Paint is not it. And so now that we have 2 here, now we know this small subproblem. Now let's expand it one more. Let's just keep expanding and expanding until we're able to sense a pattern. And so let's expand it to a 2x3. So our new box would be something like this. And now we're going to think, how many ways are there to reach this square? And only using moves of right and down, it would just be a straight line to reach there. You can go, the only ways to get into this square, rather, the better way to think about it is how many ways can you get to this square? This right here. And that would be, there's 2 ways. You come from the top or the left. But the top is out of bounds. You couldn't have reached there from the top, so only from the left. So all the ways to the left, all you have to do is add a right to it. So this is the right for this one. All you have to do is add 1 right to any of those values to get to this square. So we know that the values in this square is also going to be 1, because there's only 1 way to reach this square. And that's simpler. You don't really have to think through all the logic. If that's confusing, just think, how did we get here? There's only one way. Straight line, because you can't snake down and back up. You have to just go straight there if you want to get there. And now the next now this bottom square, this is another part where it can be tricky. When we're looking at this, we want to think how many ways, what moves could we have made to get here? And that would have been a down from this square or a right from this square. Now, we look at all the combinations to get to this square, which would be something like, here, I'll write it in the same color, which would be down and then right, down. I'm going to shorthand this. So you could go down and then right, or you could go right and then down to get there. And so that's to get to this square. But now, in order to get to the square directly next to it, all you need to do is add 1 to the end. 1 right. So all the ways you got here, plus 1 right, is how you got this square right here. And now, same thing for up top. How many ways are there to get here? You went right and right. So to denote this, we went right once, and now all we have to do is go down once, which is just going to be a D. And so I hope you can start to see that we're basing each square off of the squares ahead of it. And this approach may seem a little bit not straightforward at first, because you might just be thinking, this square is what we need. We need this square. But we can slowly work towards this square by calculating further and further values. And so the last problem, I'm sure there are recursive approaches to this, but the way we'll be talking about is, making a dynamic programming array using what I'm doing right here. This will be what our dynamic programming array will look like. And we're just slowly going to need to calculate the values through this. And so to finish it, we would hit what to finish this run through that we were doing. We'd have 1, 2, 3, and now we'd have 3 here, which is just the sum of the two before. So now that we know the rule for populating the array, which is add the square to the left and add the square above, we need to start thinking about how to implement this into our code. And I'm gonna go refer back to this because we're gonna. So in order to implement this into our code, we're gonna have an array, right? And what size we want this array to be? If we're calculating every single square in the box, like kind of what we're doing here, it would be m by n, or n by. It'd be n's on the top, so it would be n by m. So we need to declare it with a width of m and a height of a width of n and a height of m. And this will give us our thing. So for the first case, we get 7. Yeah, it's a lot. But then we would calculate n on the top and m on the bottom. Then we have this target and this target. And in order to calculate each box, we just go add this one and this one to get here. Then we add this one and this one to get here. And we just keep going. We just keep adding from the top boxes. But one key thing to note is, where do we have bounds exceptions? What are the exceptions to the rule? So the first exception to the rule was this first square. When we look in here, both of these values are out of bounds. We can't access the element beyond 0 because that would be a negative value, which is out of bounds. So we need a way to account for this. So how do we account for values that are outside of the bounds? And the answer to that is by checking if it's out of bounds. So before we test this value here, we need to check if it's out of bounds. So if the row is out of bounds, then we don't test it. Or if the column is out of bounds, we don't test it. Otherwise, if they are in bounds, we just add that to the next square. So if the top, for example, in this one right here, the left one is in bounds. So we add that to this, but the top one's not. So we don't, and we just leave it as is. And now we kind of have the pseudocode. We know the exceptions to the rule, we know the rule, and we know how we're going to visually see it. So I think now that we have the pseudo and we kind of understand the concept, I think now would be a good time to just start coding. So we already visualized our array. We're going to have an int array, a 2D int array called my array. And right now, this is just the array, but now we need to think what size is going to be. And if you look over here, it's m by n grid, and this just kind of tells us the size of the grid. It's m by n. So all we do is plug in these values here to get the length of the array. And so now we have our dynamic programming array built. I'm going to make it my DP, actually. Yeah, my DP. And the number one thing to think about is once you create your dynamic programming array, you need to populate the array. So we are creating these values and all this data inside of this array, and we need to be the ones to fill it up. It's not going to be automatically filled for us. We can't just copy values. We need to do math to find the value in each square. And in order to find the value in each square, what does that sound like? That sounds like nested for loops. So we're going to need to iterate through every single... we're going to iterate through all of the dynamic programming array. So as long as I is less than my dp dot length, and now, I guess some of you are in CSA, so this nested for loop might not be right off the tongue for you guys, but to cover what this is covering is, first we're starting in int I. This is going to cover all of our columns, and it's going to be less than the length of my DP, so this won't go 1, 2, 3, 4, 5, 6, 7. It won't go over this value out of the range, and vice versa. For the second one, we're looking at the array at 0 and the length of that, which would be n. And we're seeing, or maybe m. It actually doesn't matter. But we're looking at the value of an array inside of it, and we're making sure that this second value doesn't go outside of that. And so now we have our stopping. We know when we're going to stop populating the array, and this will iterate through every value of the array. And if that didn't make sense, this is just a nested for loop to iterate through every value of the matrix. And this is a very common concept. So if you're an AP CSA student, make sure you know how to write this, how to change it, and what each individual part does, because that'll be crucial. And this part right here is what's most confusing, so make sure you understand that. But to dive into the actual dynamic programming solution, we're going to talk about what are the base cases? What's the first example? So my DP at, the way I like to think about it is I like to think about what are we accessing in each spot. We're accessing this. This is what we want to be iterating through. So my DP at I at j is the current square we're working on. And now, hey, what do I want to do with this square? I'm thinking, okay, so I'm going to look back at my approach. For each square, I'm just looking at what's above it and to the left of it. And we're just kind of adding them. So in order to do that, we need to go my DP equals my DP at I minus 1 j plus my DP at I j minus 1. And the reason we're doing this is because we're going to see, hey, in the same row or column, let's go up 1. Okay, so this is the value here, and we're going to add this. And now in the same column, but different row, let's go back 1. And let's look at this different row, and let's add that there. And so that's the math we're doing in this equation. But the one thing we need to account for, remember, is this is the rule. But there's always going to be exceptions to the rules in your programs. And whether that's going to be like out of bounds errors or values that are extraneous, you need to make sure that you're accounting for all the possible answers. And so what we're going to do is we're going to check, how's it out of bounds? How do we know if an index is out of bounds? And that's if I minus 1, or let's look at the algorithm. Where could we run into errors? And that would be I minus 1 and j minus 1. Because these values, if 0, you would actually be running out of bounds because it's negative 1. So a better way to approach this rather than just write this all at once is going to be with an if statement. And we're going to say if I minus 1 is greater than or equal to 0. So this is if this I minus 1 value is in bounds, well, it's worth accessing. It's something we need to do. So we're going to add at So once again, this is the square on the dynamic programming array that we're accessing. And we're going to set this equal to the value of the what's above I. So because we know this I minus 1 is in bounds, we know that there's going to be a value there. And we can add I minus 1 j. And now we don't add the second part yet because we also need to check if that's inbound. So we're going to do another if statement. And note, there is no else here because if there's an else statement, then this code might not run. And it just, these are two independent events. You have no reason to use an else here. And so now we're checking, is j minus 1 greater than or equal to 0? Is this a valid, is this the valid index? And we know it, we're only checking the under as well because the over, if it's over the index length, it'll be, the loop would have been terminated. It can't possibly be over. So the only thing you can do is be under by this I minus 1. But we checked if j minus 1 is greater than 0. So we don't just want to copy and paste this entirely. We need to switch to check the j minus 1. So this first line of code, let's put it side by side, is checking, hey, we have I minus 1 is greater than or equal to 0. Is this index, is this in range? This is in range? Okay, cool. So let's check this and let's add this here. And that is this relationship right here. And the second one, we're checking, hey, is this row or this column, the other direction, is this in bounds? And yes, so now we add it. But for example, up here, we have, a top and a left, and we're going to say, hey, okay, this top thing, this is in bounds. This is out of bounds, actually. So we're going to circle it, and we know that this, j minus 1, that's negative 1. That's out of bounds. So that if statement will evaluate to false, and we'll skip that line of code. And we'll only add what's to the left of it, which is exactly what we want. And now that we have our array fully populated, this is the code to populate every square of the array and iterate all the way through it. Now, a lot of the times in LeetCode or other ways, I like to test my code by just kind of running it and seeing what happens. So what are we returning right now? We're returning, what is the point of all this? The point of all this is to find the n square. Oh, I deleted my array, sadly. But the n square is in the bottom left. And where is that the equivalent of that in our DP array? And the answer to that is in the same spot. We need to return my DP at, what is it? It's going to be m minus 1. And then n minus 1. And this will return us the last value in our DP array. And now if we run our code, we're actually going to run into an error because we never actually initialize any of these values in our array. Yeah, so it's all 0 because when we initialized our array, we never gave it a starting value. And now let's think raw base case. The very first square is the raw base case. Both these Boolean statements would evaluate to false at that square, and nothing would happen. So that's where we're getting killed. So let's think my TP at 0, 0. There's one way to get there. So we're going to set it equal to 1 because we know that there's only one way to get there, and that's by starting there. And that's our very smallest base case. And now that we have this, all the other statements will have values to add on, and it'll actually be able to start scaling. Now we run our code again. We're going to see we have an output of 1. And now let's troubleshoot. So here's the issue. The issue is that my code is setting the dynamic programming array equal to this value, when in reality we should be adding. So plus equals. Remember, we're not stealing this value. We need to account for both possibilities. So this one, it could be if it's coming from the top. Oh, wait. This is if it's coming from the top, then this one's if it's coming from the right. And so these are two separate events, and we're adding the possibilities from both of them, from the top and the right, and the left, or top and the left, not right, to find this value. And now we run our code. We should have a slightly better outcome. And yeah, so now we have our code, and it appears to be working, and we're going to submit. All right, here we go. Yeah, so we got 100% complexity. This is what you want to see. This means that your code is efficient, and if it were to scale very largely, it's the most efficient it can be. Your code's not going to overflow and die. Complexity, memory complexity, I think that's probably just due to the dynamic programming array and slight population errors. It's very minuscule, but to recover our code and recap what we did, we started by scaling down the problem. We looked at the whole problem, and we looked, hey, let's just look in just the top left. Let's look at the smallest possible example, which would be, due to our constraints, 1 and 1. And that value of 1, that's always going to have 1. So we set our very base case equal to 1. And now we base all of our other solutions off of it. So this first one, all right, I'm going to repaste this in. And so this first square we know had 1, but then, anyway, I'm going to make this big. Our first square had 1, and then our second square is based off of these values. So we checked above and to the left, we got 1, but to the left 1, 1, 1, 1, 1. Same thing down here. And now in this square, we checked above and to the left, because the only way to get here is from moving here and here. So any combination of moves to get here, plus 1 down, gets you this. And any combination of these plus 1 right equals this. And that gives us our 2 here. And if we continue this approach all the way through, we'll see that. Oh. What? This is 6, 15, 21, 28. And this gives us our final solution for this test case, which is 28. So yeah, if you have any questions about any of these dynamic programming things, feel free to leave them down below. If you want me to do more dynamic programming questions, I have some others saved up that I could cover. So yeah, just comment below what you guys want to see next, and thank you.